Welcome. Today we'll cover how to use a spectrophotometer for measuring absorbance and concentration, with tips on how to handle any errors along the way.
First, fill 2 cuvettes to the line with the pipette, one with solution and one with deionized water. Bring the cuvettes to the spectrophotometer room. Go to the program on the computer and click Scan. Clean 2 sides of the cuvette with our blank solution. Slide open the lid and place the cuvette inside, making sure the side with the arrow corresponds with the arrow in the machine. Then press the 0 button. Wait until the red script at the top corner, our absorbance, is close to 0. We zero the machine before scanning to improve the accuracy of our absorbance, and by zeroing it, we can make sure there is no interference. Remove the blank from the spectrometer. Next, take the cuvette with the solution, clean the sides, and place it into the machine. Click Start. To record the X and Y values at the lambda max.
The lambda max, or wavelength, shows us how much light the substance absorbs. This gives us the ability to know the concentration of each dilution. Finding the lambda max of a substance can play a crucial role in identifying compounds because each chemical compound or molecule has a characteristic absorption pattern in the ultraviolet or visible light spectrum.
Absorbance of aspirin and absorbance of salicylic acid are shown as the black lines. Different compounds have distinct lambda max value due to their different molecular structures. Compounds with more conjunction, more linked pi bonds, have higher lambda max value and therefore higher absorbance.
Remove the cuvette, click Simple Reads on the program, and zero again using the blank. Clean and place the cuvette with the solution in the spectrometer again. Press Read and record the absorbance value. Remove the cuvette, close the machine in the program, and carry the cuvettes back to the lab.
To find absorbance, we use the Beer-Lambert law. A equals epsilon LC. A is the absorbance, epsilon is molar absorptivity, or our extinction coefficient, C is concentration, and L is the path length. We find the absorbance using the spectrophotometer. Molar absorptivity is the slope of the graph divided by the depth of our cuvette. Path length is the width of the cuvette. We calculate the concentration using the other values. If the molar absorptivity is large, the absorbance will be high. The same happens with the concentration and path length. The higher the variable is, the higher the absorbance. To determine the concentration of our solution, we use Beer-Lambert's law. A is the absorbance of our solution, which is 0.0748 in this example. Epsilon is the wavelength, which is 500 nanometers. L, our path length, is 1. We solve for concentration by performing the following calculation to get 1.496 times 10 to the negative 4.
If you accidentally drop or spill a sample, prepare a new cuvette with the same sample solution and rerun the scan.
Accurate documentation is not only for academic integrity, but also provides evidence that you understand what is important in the lab and provides a clear record of the procedure and observations.
The importance of these techniques are to boost efficiency with each experiment, reduce mistakes and errors, and enhance focus to complete our goals.